Hello everyone, my name is Zachary Fung. Today I'll be presenting my project for the N3 NASA internship program. Uh, the scientist I work with was Dr. Fillingheim for this project, and our work was mainly focused on atmospheric ions beyond Earth atmosphere. To start off, the purpose of this project was to study the characteristics of atmospheric ions in space, as well as the types of ions there were, and the reason why they were located in the place they were located. The significance of our work was that it attempts to make connections with the history of Earth's atmosphere as well as the habitability of it. We've collected several lists of data, including mass ratio values, which all compare the concentration of particles from the sun, such as H plus or hydrogen ions, and the atmospheric ions that were drifting in space, such as N2 plus, NO plus, O2 plus, N plus, and O plus. We have compiled multiple plots from Google Spreadsheet showing the relationships between the mass ratio values as well as the geomagnetic activity indexes, which will be further explained later in the slideshow. So the data that was collected was mostly based on data that was collected or previously collected by the team at Artemis mission, which was controlled by NASA. We use specific programs, computer programs, such as virtual network computing, VNC, and interactive data language, or IDL. Both of these programs were used to mark the ions that we wanted to examine for our project. So dark red implies high concentration, as seen here, and the dark blue indicates the lowest concentration. So the majority of particles recorded in the spectrograms, such as the one shown here, originate mainly from the sun's solar winds colliding with the Earth's magnetic sphere or magnetic field. There are 4 spectrograms for each day. So each spectrogram is recorded within a 6-hour interval. So for example, one spectrogram, the first spectrogram starts from 0 to 6, next one starts from 6 to 12, next one is 12 to 18, and the final one is 18 to 24. That's how it works. The horizontal axis for each spectrogram represents the time in half-hour periods, or periods of 30 minutes each, while the vertical axis represents the kinetic energy values of the solar wind particles themselves. So some of the spectrograms actually contain a second band located by the main one, which was the main focus of what we wanted to study. This band represents the atmospheric ions themselves, which are floating around in space, as mentioned before. These ions, or majority of these ions, are often the result of atmospheric particles being caught in Earth's magnetic field, and most of these bands are often very faint visually on spectrogram, though some of them are more profound than others. So as you can see here, this band, most bands actually, that we were able to observe are significantly thinner because the concentration of the sun particles from the main band is significantly larger than those of the atmospheric ions in the second band above. Occasionally there can be a third band containing more atmospheric ions, though those cases, the cases of those happening are very rare. So for our mass ratios, we were able to find the mass ratio between the concentration of both the atmospheric ions and the particles in the sun, storing additional data through the IDL program. The mass ratios themselves were calculated through dividing the energy of the highest atmospheric ion concentration by the energy of the highest sun particle concentration. And for our graphs, we were able to, such as the one below, we were able to identify which mass ratio value was the most common out of all the other ones we recorded. So for example here, which was capturing data between 2010 and 2014, the overall majority of the ions concentrations between the sun and the atmospheric ions, most of them fell between values of 10 and 15. And these were in these sets of mass ratio values were in sets of 5s on the x-axis as shown. And lastly, for, most of these ions were containing ions such as N plus and O plus. In addition to collecting data regarding atmospheric ions, we also recorded the coordinates of the satellites responsible for recording the data. These coordinates correspond to the time when the concentrated ions was recorded. And for the data that we collected, the X, Y, and Z coordinates all have their own unique behaviors. For example, the X coordinates are almost always below 0, which means that they are almost always negative. The Y coordinates, on the other hand, have a completely different behavior, meaning that they fluctuate between being positive and negative. So they're more sparse, or more spread out, rather. And the Z coordinates, lastly, are relatively constant as values of 0. In addition to this, we also compared the relationship between two coordinates. For example, we plot the trend of the change between X and Y points, as shown here. So most of the plots match the behavior of the satellite coordinates, but other plots, as fluctuation in Y values can be seen and as X increases. So you can see the Y is constantly going up and down as X increases to the right. And this data was taken between 2015 and 2018. We have taken other graphs with different time frames, but most of them have very similar trends like this one. Now on to geomagnetic indexes. So there are 4 types: KP, DST, AE, and AP. And all of them are in charge of detecting changes in Earth's magnetosphere at different points. KP is responsible for recording the magnitude of the geomagnetic disturbance on a 0 to 9 scale. The value of 0 is very quiet geomagnetic storm, or the complete absence of one, while 9 represents an extremely profound storm. DST, however, is responsible for monitoring the variation of the Earth's ring current, which is located near the planet's equator. AE, on the other hand, is responsible for detecting changes in the Earth's auroral zone and is recorded through magnetometers, NASA magnetometers located under that zone. Finally, AP is defined as the maximum 24-hour value during a geomagnetic storm that occurs. Now, graphically speaking, the averages of these indexes were collected through NASA's Omni website. And the indexes that were focused on for this project were the KP, DST, AE, and AP indexes, as mentioned before. We were able to calculate the averages by adding the values of each index individually and dividing the sum by the number of data points within the desired time range. And based on the plot, such as this one here, there seems to be little to no correlation between the mass of the ions and the geomagnetic indexes observed. So what were our findings? First of all, we found out that most of the atmospheric ions we observed had mass ratio values between 10 and 15, which likely corresponds to containing ions such as N plus and O plus, as mentioned a few slides before. And we also found that we observed atmospheric ions across the entire magnetotail, but we observed more ions at the edges rather than near the center of it. Finally, as mentioned before as well, we found out that there does not appear to be any correlation at all between the mass of the atmospheric ions observed and the geomagnetic activity indexes. So to summarize, the significance of our project is that it connects the history of Earth's ionosphere and habitability of the planet. Through the use of Streamus Artemis mission data, IDL, VNC, as well as the Omni website, from NASA, we were able to record the concentrations of the atmospheric particles located in space. We also created graphs using Google spreadsheets representing our collected data to show any possible consistent patterns that occurred over time. And finally, we also recorded additional data such as satellite coordinates, mass ratio values between the sun particles and the atmospheric ions, and the index averages. So that was our project for the internship program. I hope you enjoyed watching this. Now, before I end this off, I would like to personally thank Dr. Fung for guiding me through this entire project, as well as its development. I would also like to thank NASA themselves for funding the entire internship program. And lastly, I would like to personally thank Dr. Kaminsky, who has provided me with this enjoyable, exciting, and worthwhile opportunity. Now, that is our project. Thank you. I hope you enjoyed it. Thank you for listening and have a nice day.